Okay, so today we're going to look at spring mass systems that are oriented vertically rather than horizontally. And the thing is, first of all, they're easy to come by. It's very easy to hang a mass on a spring and have it oscillate. But what makes it a little bit confusing is that as it moves through its oscillations, it's changing both its potential energy due to gravitation and its potential energy due to the spring. So it can be a little bit confusing, but hopefully I can help you understand it here. Okay, so if I just take a mass here and I hang it on a relaxed spring that's hanging vertically, what's going to happen is as this falls downwards, is going to convert potential energy into kinetic and eventually come to a stop. So all the energy ends up as spring energy, and it's just going to oscillate between having zero kinetic energy and having maximum kinetic energy, and having spring potential energy and having gravitational potential energy. So we're going to end up with simple harmonic motion. And the thing that makes it a little bit different is that there's both gravitational potential energy involved as well as spring potential. When it's horizontal, there's no gravitational. But we're going to see it's very similar, in fact, almost identical. Okay, so let's just try this here. It's a little bit hard to think about this. So I'm going to take a 4 kilogram mass. I'm going to hang it on a relaxed spring that's attached to the ceiling. And that spring has a constant of 400 newtons per meter. I'm just going to do this because I think it's a little bit easier sometimes to work with real numbers. And then what I'm going to do is I'm going to gently lower it until I get it into a resting position where it's just going to remain at rest. It's not going to oscillate. Well, if I do that, what I'm going to find is that since mg is 40 newtons, right, 4 kilograms times 10 is 40, then the upward force of spring force has to also equal 40 newtons. And if I look at my spring constant being 400, then I can see that this gives me a displacement of the spring of 0.1 meters. So if it moves 10 centimeters, zero point 0.1 meters, at that point here, the system is at rest. Well, the sum of the forces here is zero. And by definition, in an oscillating system, at equilibrium, the sum of the forces is zero. So I now know that the point at which I have my equilibrium is going to be zero point 0.1 meters below the relaxed state of the spring. All right. And it's going to oscillate back and forth between this. So already I can look at it and say, well, it's going to oscillate between a displacement of zero and a displacement of 0.2 because the equilibrium is 0.1. Hmm. Okay, let's see how this works. So I take this, I hang it on here, and I let it go. This is just like what we do with the falling egg, right? So what that means is this is going to fall downwards due to gravitational force, releasing gravitational potential energy until it gets to this point here. And I'm going to call that delta X. I'm going to say at this point here, I don't have any more gravitational potential energy. All my energy has been converted to spring potential energy. So I'm going to say that the gravitational potential energy of mg and this distance here, h, so that's my delta x, delta h, is going to equal the spring potential energy. So I'm going to say it's going to equal to 1/2 k delta h squared. Now, since I have delta h and delta h squared, I can get rid of one of my delta h's. And then I'm just going to multiply by 2, divide by k, and there you have it. So this delta h is going to be defined as twice the mg divided by the k. So let's see what that means in terms of this one here. So I'm going to remember when I derive this equation by equating the gravitational potential energy loss here to the gain in spring potential energy here, I get 2 mg k. So let's just substitute 2 times 4 times 10 divided by 0.2, which is what we said we'd get. So what we now know is it would fall 0.2 meters and its equilibrium point would be at 0.1 meters. So what that means then is when I put it at the top, the force of the spring is zero. The force of gravity is going to be, we'll call it in the negative direction, negative mg. So I have a net force of mg downwards. Now, I didn't like the way I wrote this, but it's too hard to change. So let's just go over here to say at the equilibrium point. When it's passing through the equilibrium point, be it on its way up or on its way down, what's going to happen? The spring force, since it's now stretched, is going to equal mg, and the gravitational force is negative mg. So the net force is zero at that point when I'm halfway through the drop. At the very end of the drop, now what I find is I've stretched the string twice as much as it was at equilibrium. So the spring force is now 2 mg, and gravity is just negative mg. So the net force is now upward mg. So look at this. It was mg at the maximum, which gives me an A of g. It was mg at the bottom. The net force was mg at the bottom, which gives me an acceleration of g. And at the middle, the net force is zero, so it's not accelerating as it passes through. So let's just put our numbers in and make sure that I'm right about this. Okay, so at the top, I have no spring force. I have 40 newtons of gravitational force pulling downwards. So the force is 40. And since F equals ma, the A is 10. Now, as it's passing through equilibrium on its way up or on its way down, what's going to happen is I have 40 newtons of spring force when I stretch it this far. I have 40 newtons of gravitational force. So I end up with zero net force and zero acceleration of this object, even though it's in motion. Now, here at the bottom, at the maximum stretch point here, now the spring force is going to be 2 times what it was here. So it's 80. This is 40. So that gives me a net of 40 up, which is the same as it was at the top. Now, here it gets a little bit tricky, but you can figure this one out, okay? What about the kinetic energy as it passes through its equilibrium point? Now, you might think, well, its equilibrium is going to equal the potential energy, but that's not the case. Let's see why, because remember, we have two kinds of energies here. All right, so it's going to fall from here. It has no spring potential energy, and its gravitational potential, and it's got no kinetic energy, but its gravitational potential energy is mgh, okay? Now, when it gets to the bottom, after falling height h, its UG is now 0, because we're defining this as the 0 point for gravitational potential energy, and it's come to a stop, so its kinetic energy is 0. So therefore, all of its energy is in spring potential energy. So even though spring potential energy is defined to be 1/2 k delta x squared, in this case, I can equate it to mgh. It has mgh worth of this. Okay, now watch. Now this is going to move up and it gets to here. Now I have 1/2 h. So if I have 1/2 h, then I've got 1/2 of my gravitational potential energy. I'm half as high here as I was here. So I have half my mgh. But I have 1/2 the delta h of the spring. And since it's the equation is 1/2 k delta x squared, if you take 1/2 squared, that's 1/4. So it's only got 1/4 of the spring potential energy here. So the total potential energy at the equilibrium point is going to be 1/2 of the gravitational and 1/4 of the spring. So that's basically 3/4 of the total energy of the system is potential, leaving 1/4 of it to be in kinetic. All right, so it's a little bit different, So if I have a horizontal block oscillator at equilibrium, the kinetic energy is equal to whatever the spring potential energy was at maximum displacement. Here it's going to equal 1/4 of that. Okay, let's just try to make sure I'm right about that. Okay, so I've got again, I have a 4 kilogram block. Spring potential, a spring constant is 400. So it's basically going to fall. We've established from here to here, which is 0.2 meters. So if I say 4 times 10 times 0.2, that gives me 8 joules. So I've got 8 joules of mechanical energy here, all in the form of gravitational potential energy. When it gets to the bottom, I've now stretched it 0.2. Now, at the bottom, it doesn't have any spring potential energy. It doesn't have any kinetic energy. All of it is going to be in spring potential energy. Let's just see how much that is. Remember, at this point, I've stretched it 0.2 meters. So 1/2 of K, so 1/2 of 400 times 0.2 squared, guess what? Equals 8 joules. All right, so now all my energy, all 8 joules, is in the form of spring potential energy. But now when I get to the midpoint here, now I have some gravitational potential energy. I have basically 4 times 10 times 0.1, which is 4 joules. And I have 1/2 of 400, that's my K value, times 0.1 squared, that's 2 joules. So the total number of joules I have here is 8 joules. Now, there hasn't been any external non-conservative force acting on the system. So therefore, I'm conserving mechanical energy. And if I have 6 joules of the two different types of potential energies, that leaves me with 2 joules of kinetic energy, which is 1/4 of the total ME of the system. So that's not intuitive, but it does make sense when you work it through. Now let's just finish up and say, well, what about the period? Okay, well, interestingly, the period isn't going to be any different because the period depends only on in a block mass system, or I'm sorry, in a spring mass system. The period of the spring is only defined by the constant 2 pi times the root of the fraction of the mass divided by the spring constant. And the mass and the spring constant are not affected by the horizontality or verticality of the system. So my spring is going to oscillate at the same period. It's going to take the same amount of time to complete an oscillation It's just that the distribution of the energies is going to be a little bit different. It's going to be traveling slower as it passes through the equilibrium point than it would be if it was horizontal. Okay, thanks for watching.